Okay, so today for mechanical systems, we're looking at topic 3, which is on energy, friction, and efficiency. Today we're going to focus on kinetic and potential energy. So work and energy, we did talk a little bit about work and energy previously. So work, it is a transfer of energy. And we talked about that we measure energy in joules. Kinetic energy is the energy of motion. So keep in mind, we talked about how energy, it cannot be created or destroyed. It has to come from somewhere. So when you're doing work on a machine, the energy is coming from the chemical energy that's stored in the food you eat. So that's where that energy comes from. And then most vehicles, for example here, they're getting their energy from fuels such as gasoline. Here we have a refrigerator. It is running on electrical energy. Okay, so just keep in mind here, bicycling, the source of energy is the person. The person is getting the energy from the chemical energy from the food. So work done, this is the amount of energy that is transferred. Work is force times distance. We talked about this a little bit already previously. Keep in mind that distance we talk about, it is the distance moved in the same direction of the force. All right, so again, work is measured in the units joules. Force is measured in newtons, and then distance is in meters. And again, it's the direction of the force. So you are able to use that formula, work is equal to force times distance, to figure out other parts. So let's say you were given work and the force, you're able to figure out distance. It would be work divided by force. If you were trying to figure out force and you were given work and distance, then you would take work and divide it by distance. All right, so you can use this triangle method. You can just cover the part you're looking for. So if you're looking for work, it's force times distance. All right, so here we have an example. You exerted a force of 22 newtons lifting a box up to a shelf 0.5 meters high. Calculate the amount of work done. Okay, so our formula for work, it is force times distance. Our force was 22 newtons and our distance is 0.5 meters. So we're going to multiply those two, which gives us 11 newtons times meters, and that is also called a joule. So that unit of work, newtons times meters, is called a joule, named after James Joule. All right, so our final statement there, the amount of work done is 11 joules. Okay, let's take a look at this example. A man tries to lift a large crate. He exerts a force of 800 newtons. The crate does not move. How much work did he do? So it's important here to remember that distance is required. So since there was no distance, there was no movement, he didn't do any work. All right, so 0 work was done. All right, so important to remember that the movement of an object is required for work to be done. So for example, another example here, if a car becomes stuck in the snow, you guys try to push it out, you might be exerting a lot of force and expending a lot of energy, but if the car doesn't move, then no work is done. All right, so here we have another example. A person does 300 joules of work to move a box of apples 24 meters. What force was required to move the box? So for this question, we are given work and we are given the distance. So we have to solve for force. So force is equal to work divided by the distance. All right, the work is 300 joules. The distance is 24 meters. So you just put that into your calculator, 300 divided by 24. And we get our answer of 12.5 newtons. All right, so that is our answer. A force of 12.5 newtons was required to move the box. All right, so next we are talking about stored energy. So stored energy is called potential energy. It has the potential to do something. So it is energy that is stored until needed. So an example of chemical potential energy would be the energy that's stored in the food or energy stored in gasoline. Gravitational potential energy is, for example, if you lift an object above Earth's surface, then it will gain gravitational potential energy. And then if you drop the object or it falls, then it will gain kinetic energy, and kinetic energy is the energy of movement. All right, so for example, here we have the energy stored in foods. So those would be the example of chemical potential energy. And then here we have gravitational potential energy. We have an apple up here, but when it falls down, then it gains kinetic energy. All right, so when it's up here, it has gravitational potential energy, and then it gets converted to kinetic energy when it falls. All right, keep in mind the apple also has stored chemical energy as well because it is a food source. All right, the water cycle shown here is driven by energy. So energy from the sun causes the water to evaporate in the first place. So here from the sun we have evaporation. That gives molecules kinetic energy. So particles start moving faster. So therefore the energy of movement that allows them to rise up into the air. And then as they rise up, they're going to slow down, and that kinetic energy turns into gravitational potential energy, the energy of height. And then just keep in mind, whenever an energy is raised up in the air, it's gaining gravitational potential energy. So therefore, water vapor is also gaining gravitational potential energy. And then when it falls, as like precipitation, it is gaining kinetic energy, which is the energy of movement. All right, so the next part of this lesson, we're first going to talk about energy transmitters. So energy, it can be converted from one form into another, and energy and power can also be transmitted. So when we are talking about energy transmission, it means that energy is transferred from one place to another, but no energy is being changed or converted. It's just being transferred from one place to another. So for example, here in a vehicle, you have a fan belt. It transmits power from the crankshaft to a fan that will cool the radiator and to a pulley that will turn the alternator. The alternator then produces electricity for use in the car or to store in the battery. So that's an example of an energy transmitter. The chain on a bicycle that links the two sprockets would be an energy transmitter. Another example would be electrical wires. They transmit the power from the generating station to your homes. So those are both examples, again, of energy transmitters. So energy is being transferred from one place to another, but it's not being changed or converted. We talked a little bit about this. Machines are not 100% efficient. An ideal machine would be able to transfer all of the energy it received to a load or to another machine, but real machines, they are not 100% efficient. There is always some energy lost into the environment. So therefore, the work output of a machine, it's always going to be less than the work input. So we can calculate efficiency. We'll do that next. The efficiency of a machine, it tells us how much of the energy that we give to the machine was transferred to the load by the machine. So here is the formula for efficiency. It's the output work, that is the work done by the machine on the load. It's divided by the input work. That's the work done on the machine by the effort. And then you would multiply it by 100 to put it into percent form. All right, so again, work output divided by work input, then we'll multiply by 100 to put it into percent form. So here's an example. I'm using an old pulley system, and construction worker raises a 2,000 Newton load by 2.0 meters by applying 450 Newton effort force over a total distance of 10 meters. Determine the efficiency of the block and tackle system, and then we have to show all our work, make sure we're showing all our units and everything. So if we look at what's being done here, again, it's the work done on the load. Okay, so again, it's the output divided by the input. And then here it's work done by the effort force. That's your input. All right, so we're going to use our formulas. That work is equal to force times distance to calculate both of those. All right, so the first one we have to calculate is work output. We'll just put work output like this. Okay, and it is 2,000 times 2 meters, which gives us 4,000. It's in joules, newtons times meters, which would be joules. And then our work input, which is 450 newtons times the 10.0 meters. So for that, we get 4,500 joules. All right, so there's our output, there's our input. All right, so now all we have to do is divide. So 4,000 divided by 4,500. Okay, for efficiency then, we're going to take our work output, which is 4,000, divide it by the work input, which was 4,500, and then we're just going to multiply by 100 to put it into percent. All right, so our efficiency, when we round that, is 89%. All right, so that's pretty high, so that would mean it is an efficient machine. All right, so every time a machine does work, some energy is lost. Like we said, it's lost to the environment, usually because of friction and heat. Machines can be made more efficient. You can reduce friction by adding a lubricant like an oil or grease. Just some downsides to using those is if there's a buildup of dirt on the lubricant, it needs to be cleaned and replaced. So again, work done on a machine, it's equal to the work that is done by the machine plus the energy that gets lost as heat due to friction. Just going to continue here. So useful friction. So like I said, friction is not always a bad thing. Friction, for example, between your bike tires and the ground ensures that the bike doesn't slip. And the friction between your running shoes and the ground. If there wasn't any friction, you'd be slipping around all the time. Many sports and outdoor activities, they also use friction in useful ways. For example, baseball players and gymnasts, they rub a powder on their hands called rosin to increase friction, improve their grip. Curling is a sport on ice. Curlers, you'll see, will sweep the ice in front of their rock, and that decreases the friction so that the rock is able to move further and straighter. All right, so friction does have its uses. So lastly, just this video on a guide to the energy of the earth. I'll pause here.